Hi, I am a second-year PhD student at the Scottish University's Environmental Research Centre, and this study is a part of my PhD thesis, which covers novel gas geochemistry of mantle plumes. And here we investigated the low helium content of the high helium to helium for Afar mantle plume. So the prevailing view is that helium to helium 4 of WAVES is higher than MOPS. This implies that the deep mantle is enriched in primordial volatiles relative to the convecting upper mantle. And the deep mantle is less degassed than upper mantle, so must have higher helium concentration. But the problem here is that high helium 3 helium 4 WAVES have lower helium concentration and lower helium 3 neon 20 than MOPS. So Anderson 1998 suggested that high helium 3 helium 4 mantle is more degassed than MOP source mantle, and this requires uranium is more incompatible than helium, and the melt residues are depleted in helium but freeze in high helium 3 helium 4. So this is difficult to reconcile with helium partition coefficients of peridotite partial melting, and this is equilibrium magma degassing, and the absence of helium concentration data in mantle reservoirs hinders the development of Earth models, of course. So before giving you the results, I just want to briefly introduce the East African Rift System and Afar plume. So the initial phase of Afar plume is produced continental fault basalts in Ethiopia and Yemen regions 30 million years ago, and these include high temperature and high titanium picrites. And Afar main Ethiopian rift basalt volcanism is generated by the upwelling mantle. So helium 3, helium 4 has decreased from 21.5 array to 16 array over this 30 million years period. And high helium 3, helium 4 basalts have narrow composition range, which is similar to high helium mantle. So despite this data, there is little consensus on the nature of upwelling mantle beneath East African rift system. Some studies say there is a huge African superplume and Afar and Kenya plumes are connected to this one. And some studies say Afar and Kenya plumes are completely different from each other. And some studies say Afar plume is originated from the transition zone, but has a continuation from the bigger Kenya plume. So our study includes helium isotopes from basalt classes from Bartol 1990 and Wonders One et al. 2015 collections. Here you can see the sample locations. And as you can see from this plot, there's a systematic increase in helium 3, helium 4 from more high values in North Red Sea to 15 array of our plume at Gulf of Tadjoura, which is located here. And this is consistent with the Afar mantle plume with geophysical evidence for mantle upwelling beneath the triple junction here. So we have a nice coherent helium 3 helium 4 trace element variation. And this along-reach helium 3 helium 4 variation is accompanied by systematic change in trace elements. So we use rubidium, lanthanum, and potassium thorium trace elements for this study. And these plots record mixing between Afar plume and heterogeneous upper mantle. So using trace element concentrations for HIMO for Afar plume and EMORP for the upper mantle, the near data here require that Afar plume mantle has 5 to 20 times less helium than the guessed upper mantle. So the low helium mantle plumes are inconsistent with the prevailing paradigm. So how can we generate this high helium 3 helium 4 but low helium concentrated Afar plume? So the simplest explanation within the prevailing model is helium-rich high helium 3 helium 4 deep mantle mixes with a proportionally dominant mass of helium pool, low helium 3 helium 4 mantle reservoir. And as you can see from this plot, if we use 1 to 4 times 10 to 14 atoms per gram helium for depleted mantle, our mantle plume must have at most 5 times 10 to the 13 atoms per gram helium. And the helium concentration of helium poor mantle reservoir is largely independent of helium 3 helium 4 and helium concentration of the deep mantle. So this is supported by a narrow range of incompatible trace elements and strontium, neodymium, osmium isotopes of highest helium-3 helium-4 Afar plume basalts. And this is also supported by geochemical isotopic similarity of high helium-3 helium-4 mean Ethiopian rift Afar basalts to the 30 million years old high titanium HD2 basalts from Ethiopian continental float basalts. So the last thing, how can we make these helium-poor mantle domains? So Afar plume signature implies on origin in recycled altered oceanic crust, likely Tethyan slab, for example. And assuming no helium recycled and established recycled altered oceanic crust uranium and thorium concentrations, as you can see from this model, to generate 5 times 10 to the 13 atoms per gram helium, we need 50 million years since subduction. For subduction rate of 20 centimeter per year and plume upwelling rate of 50 centimeter per year, the Tethyan slab has subducted into upwelling deep mantle at 700 kilometers. So the implications here, large helium-poor domains are present in deep Earth. An upwelling mantle beneath Afar acquired in shallow mantle, likely 670 kilometer transition zone, not core mantle boundary. And moderately high helium-3 helium-4 plumes like rhenium need not contain a significant contribution of deep mantle, thus cannot be used a priori to define primitive Earth composition. Thank you.